So in this example, we're going to talk about how you can determine the principal stress within for a 2D state of stress. So we're going to talk about principal stresses a little bit more when we get closer to, I think, like a 2 to 3 weeks. We're going to talk a lot about their significance and how you can use principal stresses to predict failure within materials. Um, but for now, what you need to know is that a principal stress that all you need to know for now is that principal stresses can be used to determine whether or not a material will fail under any given state of stress. So they're very critical for engineers to understand in order to predict whether or not materials will fail or will not fail. So, so if we start with our stress element, where we have our three stresses being applied, sigma x, sigma y, and tau x, and our shear stress tau x y are being applied, and we cut our stress element, in half, at some angle, which we'll denote as theta p. There'll be some angle, theta p, at theta p, where we will have a stress normal to that face, which we'll denote as sigma p, but there'll be the shear stress, which we talked about, that would be applied along that face, will not be present. Okay, um, so what we will then say here is that we would say that tau, um, uh, the shear stress along that face will be equal to 0. Okay, so all right, so at this point we could denote this. We'll call this one of the principal planes in our system. So what we're going to do is, just like we did in last lecture, we're going to just sum all the forces along the x direction and set them equal to 0. Okay, so if we do that, what we'll end up getting is we'll get, we'll say, we'll take the stress due to along the principal axis. So we'll say that to be sigma p times cosine of theta p times delta A. All right, that'll get us a total force due to the stress along the hypotenuse of this element here. And then we would have minus sigma x times delta A cosine theta p. And then we have minus tau xy times delta A sine of theta p. All right. So if we rearrange this equation, what we'll end up getting is we'll get theta p cosine theta sigma p cosine theta p is going to be equal to sigma x cosine theta p plus tau xy sine of theta p. All right. All the delta A terms will cancel out, and we're left with this equation here. All right. If we did the same thing and we summed all of our forces along the y-axis, we'd end up getting this equation here. All right. So we can combine just like last. So basically, this is the same steps that we did last lecture or during the last few videos. The only difference is that now the tau x prime y prime term from the last time, we're setting that equal to 0. Alright, so what we end up getting is, if we combine our two equations 1 and 2, what we'll end up getting, and we'll put them in matrix form, is we'll end up getting this following equation, where we have the identity matrix times sigma p times cosine of theta p times the sine of theta p, and that's going to be equal to the right-hand side of our equations, which we can simplify down to our stress matrix in 2 dimensions times our cosine theta p and sine of theta p. So if we subtract the left-hand side over and set it equal to 0, what we'll end up getting is we'll get this equation here, where we'll get sigma x tau xy, and sigma y, so our stress matrix, minus sigma p times our identity matrix times cosine theta p and sine of theta p. Here. All right. And that's going to be equal to 0. All right. So this type of equation might be familiar to you. If you looked, I think, in either your differential equations course or your linear algebra course, you should have hopefully seen something very similar to this. This is an eigenvalue problem, okay? So our eigenvalue that we're trying to solve for in this case is the variable theta p, or sigma p. Sometimes you may have, in your math classes, been asked to find the eigenvalues with I think like a underscore, I think that's a lambda that you might have been asked to solve for. So in order to find what sigma p is equal to, just like you did in your linear algebra courses to find lambda, what you would do is you can take the determinant of this matrix here, where we have our stress matrix, which is just this matrix here, minus sigma p times our identity matrix here. All right, and if we take the determinant of this equation and we set it equal to 0, we should be able to solve for our sigma p. All right. So if we do, once we obtain sigma p, we can then, so from this, what we'll end up getting is we'll get two values. We'll get one value, sigma p1, which is our first principal stress, all right, and then we'll get our second value of our principal stress, which we'll denote as sigma p2, okay? So what we'll say is the larger eigenvalue, sigma p, will denote as sigma p1, okay, and using sigma p1 and sigma p2, which are our eigenvalues, we can use our eigenvalues to solve for our eigenvectors, okay? And the eigenvectors are going to be how we can find the direction of our principal stress. So we can say sigma minus sigma p1 times the identity matrix. So sigma, again, is just our state of stress. Sigma x, tau xy, and sigma y here. All right, and if we multiply that by our eigenvector v1, we can solve for our eigenvector. All right, and then we can do the same process, and we can solve for our second eigenvector v2. All right. So in the next example problem we're going to show how you can solve for sigma p1 and sigma p2, and then we'll show, in the following video, we'll show how you can solve for the eigenvectors v1 and v2.